Hello, you absolute legends. We're going to draw a Lewis dot structure for a sulfite anion and then determine the molecular geometry of it. To start with our Lewis dot structure of sulfite, we need to determine our total electron count, the number of valence electrons that are going to be present in there. Now, if we look at our periodic table here to get our valence electrons, sulfur is only going to bring 6 valence electrons to the party. Oxygen this box represents the box that oxygen is on the periodic table. Pause for a moment and convince yourself of that. Oxygen's also going to bring 6. So we have 26 plus 6 plus 6 plus 6, 24. And then we have a -2 charge. So 26 electrons total. That is what our final Lewis dot structure can have. No more, no less. We'll start with sulfur in the center. So in Gen Chem, a lot of simple molecules have one atom in the center, and then the other atoms going around it like a compass rose, north, east, south, west. To figure out which atom is in the center, there's 2 hints that we can look at right here. The first hint is that it's the first atom written. The atom that's written first is given to the reader for usually one of 2 reasons. One reason is if it's a hydrogen atom, we're trying to tell the reader that this is an acid. This behaves like an acid. If it's not a hydrogen atom, we're probably trying to tell the reader that this atom is in the center, and the rest of the atoms we can assume kind of go around it. And another hint is that looking at the trend of electronegativity, the atom that is the least electronegative is going to be can be predicted to be in the center of that setup there. So looking at these 2 spots of oxygen and sulfur on the periodic table and knowing the electronegativity trend of increasing as we go up the periodic table, sulfur is a likely candidate to be in the center. Our simplest prediction is going to contain 1 bond. This is our simplest prediction. I've just put these oxygens on the north, east, and west. You could have put on the north and south and west. I just did this. We are now going to fill in and check the octets for each of our atoms. Don't forget the atom in the center. It's an often kind of overlooked guy right there. So now every single element has its octet. So now we're going to loop back up to the first step and make sure that we have 26 electrons total. Electrons. So this is a good Lewis dot structure with just 1 bond in between each of the atoms right there. Now to get the molecular geometry of that atom right here, we need to look at the central atom and focus on the central atom. Now in this case, the central atom is surrounded by 4 things. And just in a very broad sense right here, there's 1 thing, 2 things, 3 things, 4 things, surrounded by 4 things. So that means that the electron domain geometry is what we call tetrahedral. The electron domain geometry includes all the electrons. Big surprise there when it's called electron domain. But all the electrons, meaning that whether it's in a lone pair or a bond, we consider the electron domain geometry as tetrahedral. And here's a little model trying to show that tetrahedral geometry. It sits on the table with a triangle base. So you could think of this as a pyramid with a triangle base. To be clear, the pyramids at Giza are square base pyramids. So don't think of a square base, think of a triangle base. Another way to think about this is like a flower. Like here I'm holding the flower by the stem. And here's the flower kind of coming up. Another way I think about this is like an umbrella that you've opened too far, like you've just jammed it open. And you have the umbrella like open, the other way, the opposite way it's meant to be. So this is the electron domain geometry showing the lone pair of electrons and then the free oxygen atoms single bonded all around right there. Now the molecular geometry takes into account the bonds. So we have 3 bonds, 3 bonded things, and 1 lone pair of electrons. And when we talk about the electrical geometry, we stop thinking about the lone pair that's present, and we focus on the atoms that are surrounding the central atom there. Okay. This is a trigonal pyramidal type structure here, a trigonal pyramidal, as opposed to a trigonal planar. A trigonal planar, all the atoms lie on the floor on the base. But in a trigonal pyramidal, you see it forms that they're not all flat. There's 1 atom that's off right there. So we call this a trigonal pyramidal. Whenever you have a single atom in the center surrounded by 4 things, it takes on an electron domain geometry of tetrahedral. Whenever you have a single atom where it's surrounded by 4 things, 3 of those are bonded, and 1 of them is a lone pair, we call this trigonal pyramidal. Thank you.